Hello guys, and welcome once more to class online. Now if you have ever wondered what is the Heisenberg uncertainty principle, then you are at the right place. In this video we shall be talking about Heisenberg uncertainty principle, and we shall be clarifying it. If you've never known before, you will get to know it today. And then don't forget that if you learned something from this edition, click on like button. We have loads of content to share with you that will better help you understand physics. Don't forget that in this edition we shall be looking at Waec Physics 2016 question number 46 to 50, and we shall be destroying it. Now let's get to the question right now. Number 46 says, how many beta particles are emitted in the radioactive decay of, that is actually Au. Do you know what Au is? That is gold. Now, and it produces mercury, right? Now gold, this it builds up to mercury. Now what do you think might be correct? How many particles are absent? This is baby work. This is actually nursery one word. What's the difference between the first and the second? Do you know what it is? Now look at the numbers below. Can you see 79? Can you see 80? And that means that what? Do you now know? Now that's just it. That is correct. So the simple answer is that the difference is between 79 to 80. The ones above are actually the same. So the simple answer to the simple question is just this. The amount of the beta particles are just one. Now look at this picture for a minute. Now we have here gold producing what? Mercury, right? Now the gap is not in their mass number. The difference is rather in their what? In their atomic number, and it released one electron, which is a beta particle. So it released an electron in between. So one electron was lost. Now can you see this? Now can you just look at this? Look at uranium, okay, and then producing what? Thorium. Can you see thorium? Now how many electron was lost? Just two. It actually threw out two what? Helium electrons. So that's, we have helium, 2 for heliums, right? And that's just it. So on and on, the simple answer to number 46 is just ask my baby. The baby, even babies can do this. This is just one, and that's the simple thing about this question. Now number 47 says the phenomenon by which two light atoms nuclei combine to form a heavy nuclide with the release of energy is known as what? Now do you know what that means? Do you have any idea? And have you heard about what they call nuclear fusion and nuclear fission before? Now if you haven't, I'll tell you. Now that is actually when two light substances, okay, nuclei form one heavy nuclide. Okay, that is actually an example of nuclear what? Fusion. And I'll tell you why. Now this is where you'll get to learn it now. Now we know that nuclear fusion is the process by which a single heavy nucleus, okay, part of an atom from it's the process of making is the process of making a single heavy nucleus part of an atom from two lighter nuclei. Now fusion happens in the middle of stars like the sun. Hydrogen atoms are fused together to make helium. These release lots of energy. Now okay, now look at this. Now fusion is the process whereby smaller nucleuses or nuclei, that's plural, form a single nuclide. I'll come again. Like you have smaller stones forming a big mummy stone, big stone. So when little stones form one giant stone, that is nuclear fusion, because they are fusing into one. Okay, and in the process this releases a lot of energy. Like what you have there is what you have, an example is the stars forming the sun. When the stars come together, they form the almighty sun, right? So many stars create one. That is, they fuse and they form the sun, and that is nuclear fusion. Now nuclear fission, and that means that nuclear fusion is the answer we are looking for, because it's the process whereby two light atomic nuclei combine to form a heavy nuclide, which is the release of energy, and that is nuclear fusion. So fusion is our answer. But for the sake of next time, let's learn the others. What is the meaning of nuclear fission? Fission is the opposite. When one breaks down into many smaller ones, that's fission. Fission is never the same as fusion. Don't mix fission for fusion. Now fusion is smaller ones creating a bigger one. Why? And that thing, of course, that I said as one is nucleus. Smaller nuclei, that's plural of nucleus, produce one nuclide, and that is fusion. But when one breaks down into many smaller ones, that is an example of nuclear fission. Fission is a nuclear reaction or radioactive decay process in which the nucleus of an atom split into two or more smaller lighter nuclei, and that's what we have there, nuclear fission. Now, fission is the process. I always say that fission is one of the process for making bomb, and that is what you have when you have one particle split into many, and the splitting releases energy. Okay, now it releases energy in the process, right? It releases energy in the process because when bomb splits, it breaks in from one mass into smaller particle. And what do you feel if you are you can see in movies when bomb explodes, people are thrown off balance, right? That is an example of nuclear fission. One breaks into many and it releases energy out, and that is an example of fission. It releases nuclear energy. Now, radioactivity, we know, is the phenomenon of the spontaneous disintegration of stable unstable atom nuclei towards atomic nuclei to form more energetic stable atomic nuclei. So it is the breakdown of unstable nuclei, okay, to form stable nuclei, and that is just radioactivity. It is the spontaneous, that's continuous disintegration or breakdown of unstable nuclei to form stable nuclei, and that is it. Then chain reaction is actually under nuclear fission. It's a part of nuclear fission. You know, it's a chemical reaction or other process in which the products themselves promote or spread the reaction. Now I won't go on. Now, chain reaction happens under nuclear fission. When things disintegrate or break down, that's nuclear fission. Okay, in the process, if one breaks into two breaks into four, 4 breaks into 8, that is a chain. That is called chain reaction. So when the product produces another product, it's an example of chain reaction. But the answer to the simple question is just nuclear fission, and that is just in nuclear fusion. Nuclear fusion, and that is just the simple answer to the simple question. Number 48. Which of the following graph is correct for the decay of radioactive substance with a half-life of 2 years? Now take a look at that now. Now we have the first one. They look similar, but now no, they are not similar. Look at this. Look at this. It's not the same. Look at this. It's not the same. Look at this. It's not the same. Now you may be saying that these are the same, but no. This is in contact. This is not in contact on top. This is not in contact below. This is in contact up and down. What do you think might be correct? Do you have any idea? Now actually, the correct answer I will tell you is this. And the reason is because half-life has to do with years, number of years, right? That's years, and the number of disintegration or decay. It has to do with a decay constant. As 2 years, half-life of 2 years. Now, if 2 years is the half-life, this is the 2 years, but it mustn't come in contact with the number of years. In the graph of half-life, we don't draw it to be in contact with the number of years below. So the answer to that question is simply option C. The fraction of radioactive isotope observed in this spectrometer decreases exponentially in time, while the mass of decay product with boron for carbon-10 will gradually increase. So this is explaining how the graph should be drawn, and this is the way it is. So as the mass is increasing, okay, this one is sloping down, is decreasing. So that means yes, time is decreasing, while the mass is increasing. This is the mass here, starting from my hand, and my time is my t here. So this is going to help to explain that, and that is how we got C as our best answer to number 48. Now maybe in a later video we'll dwell more on that, but for now we are dealing with just past questions, so we have to move on from that. If you have any question, don't worry, we'll soon work on videos that will address radioactivity or what's it called, half-life as a topic. Now let's check out number 49. In a p-type semiconductor, this is actually a semiconductor topic, right? The dash A, number of holes are equal to the number of electrons. Is that always true? No. Is that true for a p-type? No. The electrical resistivity increases. Is that true? Then electrons are the majority charge carrier. Is that true? Holes are the majority charge carrier. Is that true? Now there's one thing to know about, we have what we call n-type and we have p-type. Now there are two types of semiconductors. One is n-type and we have the p-type, right? Now under this topic, now you must know that the p have surplus of O. Generally, that's the first understanding we have on this topic, that the p semiconductor have surplus of O, while the N have surplus of negative electrons. Just say electrons, don't just say negative. Electrons are always negative. Now P has surplus of O, while electrons have surplus of electrons, and that already answered our question. But for the sake of broader understanding, a p-type semiconductor is a type of semiconductor. A p-type semiconductor has more O's than electrons. That has been said here. This allows the current to flow along the material from O to O, but only in one direction. So the P flows in one direction. Okay. Now, semiconductors are more often made from silicon. Silicon is an element with 4 elements in its outer shell, and that is the p-type. It's made from semiconductors. It has aggregates of O's, not electrons, but O's, and it flows. Like I said, it flows in one direction, and the answer is therefore the O's are the majority charge carrier. Now, if it were N, it would have been C. Electrons are the majority charge carrier. If it were, but because it is p-type, it is not n-type. It is now O's are the majority charge carrier, and that is the answer for that question. Now we come to S symbol. Now the change in S. Let's change in S be the uncertainty in the situation of position, and change in P the uncertainty in the measure of momentum, right? Then the uncertainty principle relation is given as what? Now, you've heard about this guy called Heisenberg in science before, right? Now, Heisenberg is a scientist, is a German, is a scientist that postulated the what we call the Heisenberg uncertainty principle. And that principle is very, very simple. The principle said that it is impossible to precisely state the position and momentum of a body. That's just it. It is impossible to precisely measure the position and momentum of a substance. It is now, that means, in science we also that the position of this thing is at coordinate 2 minus 3. That's on the x-axis is 2 and the y-axis is minus 3. Okay, now that's a position, right? But Heisenberg said that position is not precise. Okay, so Heisenberg was fighting that we can't really know the position of something exactly, precisely. We can't really give the coordinate perfectly in science. Science can't really give the coordinates of an object fully. That's precisely without any error. Even in the position that we give, there are still little alterations. There are still little errors. So you can't give the position and you can't give the momentum. Know that. So Heisenberg simply says that the position and momentum of an object cannot really cannot be precisely measured. That means cannot be measured precisely. That means you cannot measure it without any error. It's not possible to measure the position and momentum of an object without error. It's not possible, and that's what we call Heisenberg uncertainty principle. And therefore, the answer is just this one: position and momentum times momentum is greater than what? H. What's my H? Planck constant over 4 pi, and this is the Heisenberg formula. But the principle is what I said, that the position and the momentum of an object cannot be precisely measured, and that is Heisenberg's uncertainty principle, and that is the answer. So this is greater than, and that makes this one to be the correct answer to that question. Full stop. And that brings us to the end of this video. Don't forget, if you learned something from this video, we have loads of content that will better help you understand physics, and you might want to press the like button or tell your friends about it. We have much to share with you that will better help you understand physics. Until we see you next time, guys, take care of yourself and bye for now.